Welcome to Excel 2010 Statistics video number 68. Hey, if you want to download this workbook, Business 210 Chapter 7, or the PDFs, click on the link below the video. In this video, we got to talk about the sampling distribution of sample means, or the sampling distribution of Xbar. That means, actually, a few videos ago, we talked about a population, a sample, extracting some data from the population into our sample, and then calculating a mean. So here, a couple of videos ago, we calculated the mean from our sample. We also calculated our population mean. And there is a difference, right? The difference is called sampling error. Now, this is randomized. So as I take a sample, this number will change. If I hit the F9 key, you can see now Xbar, the random variable, is above. Now it's just slightly below. So we want to talk about sample mean, or Xbar, as our random variable. And what if we plotted, we had the population of all of our Xbar, what would the distribution look like? So in this video, we're actually going to build what's called the sampling distribution of Xbar. From that, we will be able to then explain whether or not our sampling error is reasonable or not. Now, we're on this sheet that we already did this a few videos, population sample. I want to zoom way ahead. I'll show you a great trick here. If you right-click these scroll arrows for the sheet tabs, right-click, it'll give you a list of all the sheets. And we want to jump to the one SDO Xbar, which means sampling distribution of Xbar. Now, we're actually going to use a very small data set. And then in our next example, it'll be a little bit bigger, so that we can actually manually build our sampling distribution of sample mean. Now, this is not anything you would do out in the working world. But what we're going to do in this video will help us understand why what we do with the sampling distribution when we're doing hypothesis testing and intervals and things like that later, why all of that is true, or why we can do that. All right, so here's the population. We have some partners in a law firm, and here's the hours they worked. Now, if we could take samples from this, we're going to say sample size 2. Again, this is just an exercise to understand the sampling distribution of sample mean. But what if we could take all the possible samples of 2 from this population and then plot them? What would that look like compared to the plot of the population data? Not only that, but what would the mean? So it's easy to calculate the mean, or the Xbar, from the population data. But what would the mean be of all the samples? So those are the two things we want to do here. Now, the first thing is, let's count how many items we have in our population. I'm going to use the count function. That'll allow us to count numbers. So there's 5. Now, in order to figure out from some number in the population then all the possible samples, we use the combination formula. And in Excel, it's the combine. So equals combine the number and the number chosen. The number is going to be the number of items in our population, comma the number chosen, that's our sample size. This calculation will tell us how many total samples are possible. So 10. Again, the reason we did a small sample like this is because we can force our way through calculating 10 different samples. Whereas if it was anything bigger than 5, then this number is going to get very big. All right, let's scroll down here. Now, in earlier chapters, chapter 4, 5, you had to actually list all of the possible sample points. So I did that. I took all the possibilities here. Done is matched with Hardy. Then done is matched with Kurz. Then done is matched with Mallory. Then done is matched with Tillman. And I went ahead and listed that all here. Now, what I want to do is, we're not going to do calculations on the names. We want to do calculations on the hours. Remember, if we're taking a sample, Dunn and Hardy, of the number of hours, we're going to calculate an average. Once we get all of the possible averages from sample size 2, we'll actually calculate the mean of all the means, and we'll come to an amazing conclusion here. Now, I don't want to, you could do this manually, right? Done equals 2. Tab. Hardy equals 26. Done equals 22. Tab. Cures equals, and then get this. Well, this takes a long time, and it's prone to errors. So instead, we're going to use the VLOOKUP. Now, VLOOKUP is great. It is a lookup function. You could say, hey, VLOOKUP, go look up Dunn's name, find it in this table, and then bring this number back to the cell. When we're over here, we'll say, hey, VLOOKUP, look up Hardy. The VLOOKUP will go look up in the first column of this table. It'll take this 26 and bring it over here. All right? So you're ready? In this cell right here, I'm going to say equals VLOOKUP. Now, VLOOKUP is a great function, and the screen tips are quite handy here. And the logic of how this function works follows exactly how we do it in real life. Now, when we do it in real life, we take the done, we remember it, we go over here and find it, take this matching value. So the first thing you have to do for the VLOOKUP is say, hey, what is it that you want to look up? I want to look up done. Now, this is going to be a relative cell reference. As we copy over here and down, the dancing ants will move to each new name. Comma to get to what? Well, if you're doing this by hand, you put done into your memory, and then you know where the table is. So you look there, right? Well, VLOOKUP doesn't know where the table is. You have to tell it. So you highlight the table. F4 key to lock it, because wherever we move this VLOOKUP formula, that table's got to be locked. Now, important, this value right here is a word, and that the first column of any VLOOKUP table is the column that the VLOOKUP looks through. All right? Comma. Like if you had done Hardy cures over to this way, you couldn't use the VLOOKUP. Comma. Now, column index. Look at what we do. We put this done in our brain. We go over to the table. But as soon as we find done, what do? We go over to the second column to get the value to bring down to the cell. So you have to tell VLOOKUP which column it is. It's in 2. Comma. And finally, you have to say whether it's an approximate match. That's for taxes and commissions, or exact match. We're doing an exact match here. I want to find exactly done. Now, false is equivalent to 0, so I'm putting a 0. If you were putting a true, it would be 1. That little formula right there. Just amazing. Control-Enter. Copy it over and down. And lo and behold, did it not perfectly work? That is just amazing. There's if you can't, there's lots of great uses for the VLOOKUP. All right, now we have all of our possible samples, all the people, and there's the numbers. Now let's come over here and calculate the average. Relative cell reference, Control-Enter, and then copy it down. All right. Now, so we have all of the possible sample means. Now, so what are we going to do? We're going to plot these and see what they look like, right? This is not x. The x's were these actual hours. These are averages. Now, anytime you do an average, it's always going to be towards the center, because an average, if there's extreme values, the averages are never going to be one of the extreme values. So I don't know if you notice here, but it looks like the range is like between 24 and 28. Whereas if you look over here, the range is like between 22 and 30. So, but OK, so these are all averages. Let's calculate the average of all the averages. So equals average. I told you in just a moment we'll see something so amazing about averages of all the averages. All right, so 25.2. Now, in a moment, we'll plot this, remember, because we have to see what it looks like, right, if we're going to use the distribution of sample means. That's the value that's going to be in the middle. All right. Now, let's compare this. Let's just, for kicks, let's calculate the mean for the population. So I'm going to go equals average. And it's all the way up here, so I'm going to scroll over. It's just these values right here. All right, drum roll. You got to be kidding me. If it's possible to calculate all the sample means and then take the mean or the Xbar of all of the Xbars or the means, it'll be exactly equal to the population mean. That is amazing. That means if we know the population mean, like if you have a box of cereal that you're filling and it says 14 ounces, the population mean should be 14 ounces. So you oftentimes know what the population mean is, or you should know. Like someone makes a claim. The claim is these tires will give you 35,000 miles. So that's the population mean. So you have oftentimes know this. But now, since you know that, you also will know the mean for the distribution of Xbars. All right, so that's conclusion number 1. And actually, if we go over to the PDFs on slide 16, the expected value of Xbar, or the mean of the Xbars, of sampling distribution of Xbars. This is always the case, right? You could, in our textbook, they say expected Xbar. Another notation is mu sub Xbar. That just means, hey, what's the population mean of all the Xbars? I like this notation better than this one, but they use this one in this book. And guess what? It'll always be equal to the population mean. Oops, I have to go back to, I think it's 16, right? Right, and all that says here, if we're able to select all the possible samples of a particular size from a given population, then the mean of the sample distribution of Xbar is equal to the population mean. Now, that's conclusion number 1. Remember, we are doing this exercise here to learn something about the distribution of Xbars. All right, now let's come over and plot these. Now, I actually already have some pictures here, but let's just go ahead and plot these. Now, this goes back to chapter 2. We have from our population, if we go up here and look, there's a 22, a 26, a 30, a 26, a 22, right? So we're just going to do count if. And that'll give us our count, and then we plot it. So count if. The range is going to be this range of population, and then hit the F4 key, comma, and then this. And then you copy it down. All right, so we got a 2, 2, and a 1. Now let's go ahead and do the distribution, frequency distribution for the sample means. Now, when we looked up here, here's all of our sample means. We just took all the possible answers we got and listed them here. This is a unique list, and now we're going to count. I'll go up and get that range there. F4, what's great about F4 is we need to lock it in. It jumps the screen back in view, comma, and then there's the criteria. Control-Enter and drag it down. Now, when you plot these, which I already did, we want to look at the distribution, right? So looks like it's skewed towards the left, or positive skew, right? And it almost, I mean, it's uniform right here, and then there's one big value up here. Now, again, this is a small data set. In just a moment, I'll do this on a bigger data set, and we'll see even more dramatic conclusion here. But notice what happens for the distribution of sample means. It's already looking more bell or normal shaped. Now, this shouldn't be too surprising because these are averages, right? It's averages that we're plotting. Now, so conclusion number 1 was that population mean equals mean of the sampling distribution of sample means, or Xbar. Conclusion number 2 is, there we go, sampling distribution of sample mean tends to be normally distributed. That means if a random variable is Xbar, then we can use the standard normal curve for comparison. Right? Not only that, but there's less spread in the data, right? This goes from 22 to 30. This one goes from 22 to 28. Now, again, this is a small data set, so the differences aren't too much in it. We'll see a bigger data set in just a moment where the differences are much larger. Now, this is going to lead to something totally amazing. The central limit theorem. And here it is. If all samples of a particular size are selected from any population, the sampling distribution of Xbar is approximately normally distributed. The approximation improves with larger samples. Now check this out. If the population distribution is symmetrical but not normal, the distribution will converge toward normal when n is greater than 10. Again, n has to be randomly selected. You've got to be kidding me. You mean we only have to have a sample of 10? Yeah. Skewed or thick-tailed distributions converge towards the normal when n is greater than 30, right? So if you have a sample size greater than 30. Even heavily skewed distributions tend to be normally distributed with n greater than 50. Now let's go down, go back to our PDFs, and we'll see something totally amazing. Let's say slide 21. This is from our textbook. Let's see if I can scroll down here. So here's the populations, right? This one looks like a skateboard ramp, right? Oh, this looks like a skateboard ramp. And this one too? No. OK, so this is a distribution. Here's another distribution. Here's our uniform distribution. Here's our exponential distribution. These are heavily skewed, right? But look what happens at n equals 2. That means our sample size was 2. Down here, n equals 6. Or here, look, even all heavily skewed in some direction or non-bell-shaped, non-normal shape, when the sample size gets to be 30, then look at this. They all tend to be normally distributed. That means we're allowed to, no matter what the original population distribution is shaped like, we can use the standard normal curve. Now let's go back over to Excel here. I want to do another example. And let's see, standard sampling distribution of Xbars 2. Now this right here, we have this small data set. Now how many are there here? There's 17, right? In our first example, we had 5. And here are some numbers. So we want to actually see if we can list all the possible samples. All right, now down here, I'm going to say how many combinations. We're going to have a sample size of 4. So I'm going to say n equals 4. And then COMBIN. Whoops, that's got some number formatting. Actually, let's do this right here. We'll go pop count, which is n, right? I'll do it this way. And then population count will equal big N, right? That's our notation. Equals count. Count all these. Should be 17. All right, let's figure out all the combinations, and then we'll see if we can list them all. OK, so the number is the population size. The number chosen is the sample size. 2,380. There's no way. That means I'd have to take Joe listed with these 3, Joe listed with these 3, Joe. Oh, that would take forever. But luckily, I went ahead and did it already. There is control down arrow. There are 2,380. So again, our goal here is we want to somehow prove to ourselves that it's all right to use the standard normal curve when we're taking samples. All right, now we're going to do our VLOOKUP to extract all of our numbers to calculate our mean for each sample. So I'm going to say, hey, relative cell reference, comma, that's our lookup value. The table, it's going to be this table right here, F4, comma, column, it's going to be 2, this 2. The second column has our number, comma, and we're looking up an exact match, so I put a 0. So Control Enter, and then I'm going to drag this over and double click and send it down. Now that really is the power, right? Because we would never be able to do that manually. And sure enough, all the way at the bottom, and that VLOOKUP is just working perfect. All right, now let's calculate the mean. Control Enter, double click and send it down. I hope I didn't send that too far. Now I've already calculated, just like we saw just a few moments ago, I calculated the mean of all the means. I got 64,252. And over here I calculated the mean B3 to B19 of our population data. And of course, we come up with our same conclusion we saw in our smaller example. Well, that's not surprising. The next little thing is probably going to be even more helpful. now that we have a large data set. Let's go ahead and we have our salaries ranging from 13,000 to 108. So I just built a little table. Just like in Chapter 2, we can use the count ifs with an S function to calculate the count, the frequency table, and then we'll plot it. All right, so count ifs. And our first one will do the population. So I'm going to go over and get my population data. F4, comma, the criteria is going to be in parentheses greater than or equal to, close parentheses, ampersand, below, comma, I'm just going to copy this right here because we have to list it twice in countifs, comma, and then less than. Notice I'm not putting the equal sign here. I'm not including the upper end. So we have our formula for counting between an upper and a lower. Control Enter. Double click and send it down. So there's our count. Now let's do the same thing. Watch this. I'm going to cheat. Copy. Now that would give me the same thing, but I'm going to highlight this range right here. I'm not even going to hit delete. I'm going to come over and Control Shift down arrow F4. Now I have that range there. Copy, and then I'm going to put this range right here. Control Enter, double click and send it down. Wow, OK, well that makes sense. But now let's plot these. Now I put some labels here. I'm going to highlight this, and we want a column chart. I'm going to use my keyboard shortcut Alt F1. That's the default chart. I'm going to delete that. Maybe delete these lines. I don't even care about that. I'm going to highlight a column and Control 1. No gap width. And I want border color solid and black. All right. So and then I can decrease the size down. That's pretty straight, uniform. Not quite uniform, but it's definitely not bell-shaped. Now let's do the same thing here. Now watch this. I need these labels and this, so I'm going to highlight one column, then hold Control and get the second column. Alt F1. Delete. Delete. Remember, we did a lot of this back in Chapter 2. Select the columns. Control 1. No gap width. Border color solid. You got to be kidding me. Look at that. Scrunch this in. I mean, this is live, right? We saw the picture from the textbook, but here we did our own little experiment. So it just means that this population data is like a rectangle almost, right? And yet, look at what happens when we plot all of the possible means. That's looking pretty bell-shaped. Now, Chapter 6, we saw how we could then take a particular x and using probability say whether it's reasonable that we'd get this. So now, the fact that this is bell-shaped will lead to the central limit theorem. We can go out and take samples and compare it to our standard normal curve. Now, two last things here. Notice here that it looks like it goes from 20,000 up to the 100,000. But over here, it looks like it's going from 10 to 110. So from this picture, you can see it looks like there's a little bit more spread in the population data than in the distribution of sample means. Now, that should make perfect sense because population data can have the extreme values, right? Whereas the averages just aren't going to have those because they're averages. You're adding them all up, dividing them by the count. You're always getting some central tendency number. Now, we're going to go over to two things. We're going to go back to our PDFs. In the PDFs, it says page 14. It's actually page 17 because there's two title pages. All right, so we need to figure out what the standard deviation of the sampling distribution of Xbar is, or it's called the standard error. Now, for infinite population and a finite population, we have slightly different formulas. Now, let me scroll down here. These are both to calculate standard error or standard deviation of Xbar. This is what you use for infinite population. When you get to finite population, you have this correction factor. Now, and we'll test this when we do our three examples. When you have sample size divided by n, is less than 0.05 right here, then simply use, oh, exactly this. So these two are what, and the fact the textbook assumes that these are always going to be the same. So even for finite populations where the population has some huge number, usually sample size is very, very small. So this, when you do this calculation, it's less than 5. When it's greater than 5, then you have to use this correction factor. All right, now why are we taking sigma and dividing by some number? Well, this is called sigma sub Xbar, which is the standard error. The picture, you see the spread is less, the spread is more. So by taking the square root of n in the denominator, it reduces it just enough so that we have a standard deviation for our distribution of sample means. And we'll see a couple examples of how the distribution changes and the standard deviation for the distribution changes as n changes in later videos. All right, the last thing we want to go to page 20. And the long and short of this video, sampling distribution of Xbar and the central limit theory. This all will allow us, we can reason about the sampling distribution of Xbar with absolutely no information about the shape of the original distribution from which the sample is taken. This means we can use our functions, norm.s.dist and norm.dist, to test whether our samples are reasonable or not. Now we're in chapter 7 here. We'll again use this 7, 8, 9, and 10. All right, next video we'll actually see some examples of how we take our sample mean and test whether it's reasonable or not. All right, see you next video.